the slide, yeah? Let me know. So 5.2 today. Five point two. Please look at the slide 5.2, yeah? I will highlight using the snapshot 5.2. Finite difference method for heat conduction equation. So in the previous lecture, you saw elliptic equation, type of PDE, partial differential equation. Yeah. So today we will go into a detail about the method, finite difference methods. So, but these finite difference method can solve one particular problem, that is heat conduction equation, which is very important in engineering. So heat conduction equation is one of the famous important partial differential equation. So last week we just saw the general introduction to PDE, partial differential equation. Today we will try to move on to a method, but this method is very general, finite difference, and we will look into more detail. There are a few sub methods, sub methods involved under finite difference. So there are altogether 54 slides, but today we will try to do very few so that next week we can continue. So the slides are not available at ULearn at the moment. So what you do, you copy the important points. So you can take a piece of paper because we need to do some calculation. These are the numerical experiment whereby you can use your calculator to do a simple calculation. Because this is not analytical method like what you have done in chapter 3, Laplace transform, Wronskian, undetermined coefficient, Bernoulli, linear, exact equation, separable, and so on. It is similar to Euler, Young's method, and then Runge-Kutta. But Runge-Kutta, Euler, Young's method, these are what you saw in chapter 4, solving first order ODE, ordinary differential equation. So solving ordinary differential equation by using Runge-Kutta and Young's method and Euler method is not very difficult because it involves only initial condition. But here you can see the difference. The difference is you will see boundary condition, initial boundary condition, and then initial condition. So it is a combination of boundary condition, involves the boundary as well as initial condition. So this will involve a lot of huge number of calculation. Basically, we call this as iteration. Yeah, iteration. You have to do many iteration in order to find the solution. If any problem, please let me know. You can type on the chat. If the slides are not clear or slide is not moving, so we will upload again for you. Now, I will go very slowly because you have to take down the notes. You can take a photograph or write down. If I am very fast, you just let me know. I will pause for you so that you can copy, yeah? And you can do the revision. So what is finite difference method for solving heat conduction equation? So first of all, we want to see the learning outcome. FD stand for finance difference, because this is the shortcut format. Very much we use a shortcut form, which is very nice to see and easy to remember. Easy to remember, easy to recall. So that's why they use the shortcut, what we call the acronym, or we call it notation or symbols, things like that, which is very famous in engineering mathematics subjects. So what we want you to do is, at the end of the session, should be able to solve. But we are not going to solve today the whole thing. Maybe we will cover 50%, and then we will continue next week, the rest 50%. So solve the heat conduction equation by using finite difference methods. So the objective is very simple, straightforward, single objective: solve heat conduction equation. So first you must know the format. We have to identify the format of heat conduction equation, and then we will move on to finite difference method. And finite difference method is a very huge area. So we just cover one or two methods. Basically, maximum 3 methods involved in these finite difference methods. So that's why we call it sub methods. Now, slide number 5 here. So the finite different methods. First, the heat conduction equation can be solved by substituting. This keyword is substituting. Substituting.
Hello, sir. Sorry for
Yes.
interrupt, but
Yeah.
the slide is not moving.
Slide is not moving.
Yeah.
Okay. Okay. All right. So wait a minute. That is the problem we are facing. So I will. Who is that just now? The slide not moving. Okay. So
Patricia.
I will upload again. Okay. That is the problem we are facing now. Okay. Okay, I share again. Okay, we are now in slide number 5, yeah? Now we are at slide number 5, huh? Yes, one. We already shared the slide. One, can you see the slide? Okay. What about Mohammed Dennis? Mohammed Dennis? All right, thank you. Okay, what about Patricia?
Yes, sir.
Is it okay?
Yeah, okay already.
All right. So at any moment, if the slide is not moving, let me know. So I will cancel the stop sharing and then upload again. I mean share again, because on my screen it is written there stop sharing, and after that I will share again. All right. So here is the thing. The finance different method that you're going to study got 3 parts. But the Crank-Nicholson method is not involved, not available in this file. So maybe next week we hope the chapter 5 will be uploaded via ULearn. So at the moment it is not available. We are sorry about that. So you have to wait for the full notes. Maybe next week, week number 10 or 11. So we are now week number 9, right? So we have 3 more weeks to go. So what we will do in this session, we will do finance different methods, explicit method, first one only. And then we will move on to simple implicit method. You know, explicit method, this is in calculus, we say explicit function and then implicit function. Explicit function like y equal to fx. Y is the output, x is the input. This is explicit. Implicit, x and y together. So this finance difference method involve explicit method, simple implicit method, and Crank-Nicholson method. These are the methods we got to study one by one because all these are interrelated or interconnected. We will see later. So this explicit and simple implicit Crank-Nicholson are the method to solve the heat conduction equation in this session. But this heat conduction equation is one type. You saw there are 3 types: elliptic, parabolic, hyperbolic. Wave equation, Laplace equation, heat conduction equation. You can use this method to solve wave equation as well as Laplace equation. So here we are just showing you one example only. So our focus is on heat conduction equation. Can be solved by substituting finite divided differences for the partial derivatives. So this is at the moment is not clear because you have to look into the problem. We already show you the problem statement in 5.1. So we will use that and then redo again because it is not completed yet. So we will show you again the same problem and then we solve using the first method, explicit method, and then move on to simple implicit method, and the last one is Crank-Nicholson method. So for the heat conduction equation, we must consider change in time, that is small t, and then space, that is the x. So the temperature variable T depend on time and x distance. That is capital T. You remember we gave you the equation for the heat conduction equation. Del T over del T equals to K del square T del x square. We will show you that again. So this explicit method, so we will not go into a detail how it was developed, the background. What you see in the slide number 6 is the left hand side is the partial differential equation. The right hand side is the numerical calculation. It's already proven. So we just quote this partial derivative in terms of numerical formula. That capital T, we are referring to the temperature, and the terms all will be explained later. So you just have to wait, yeah? Just follow the slide, and we have the name for it. Under explicit method, there are two equations. One is for the temperature respect to distance, capital T respect to x. That is what we call centered finite difference equation. The other one is forward finite difference, temperature respect to time. So this del squared T del x squared is the left-hand side is the PDE, partial differential equation. The right-hand side is the one that you are going to do the calculation later. But now at the moment, we just code only. What is that? The terms, the symbols, we will explain to you later. So the right-hand side, T superscript L, subscript I plus 1, minus 2T superscript L subscript I, plus T superscript L subscript I minus 1, the whole thing divided by del x squared. The del x is the last time you call it step size for the distance, but we call the difference for the distance, del x. Later, I plus 1. So this value we will substitute later. We have to substitute and we will calculate. So all this value, capital T, but the I plus 1, we call this as next temperature, T, I plus 1. The Ti is the current temperature, T subscript I.
Sir, sorry for interrupting again, but your slide is not moving.
You are now in which slide? I'm number 6.
Slide number 5.
Not moving.
Yes.
What about others? Slide not moving. So is the problem, huh? Okay, I'll try to upload. Okay, can you see the slide now? Now? Okay, Purushothaman. Okay, thank you, Patricia. Gabriel Tan. Okay, slide 6 now. Okay, quickly you write down this equation, class. Del squared T del x squared, write down, yeah, equals to T superscript L subscript I plus 1 minus 2 multiplied by T superscript L subscript I plus T superscript L subscript I minus 1, whole thing divided by del x squared. Please write down, yeah, because we need this equation. This equation is already well established. So it is available and we use this equation to perform the numerical computations. So we are not going to calculate the left-hand side. The left-hand side will be calculated using the right-hand side. The value solved will be given later. You will see how we perform the numerical experiment. Now, as you So in the previous lecture, the heat conduction equation involved del squared T del x squared del T over del T. The pronunciation still same because the capital T temperature, the small t is time. So del T over del T equals to T superscript L plus 1. This is L plus 1 subscript I minus T superscript L subscript I divided by del T. So this is the forward finite difference. So we use these two equations to solve the heat conduction equation. So you write down these two equations. Equation number 1 is for del squared T del x squared. Equation number 2 for del T over del T. So what is important here is you must understand what is this terminologies. Del T is the small difference in time. Del T is small difference in time. Liu, slide number 6, yeah? And now we move on. Once you already write down these two equations, now we move on to solving this equation. This equation can be solved analytically, but that is you have to study under numerical analysis. But we are solving this very famous heat conduction equation using numerical method. So now you substitute del T over del T equals to T superscript L plus 1 subscript I minus T superscript L subscript I divided by del T. You just substitute. This is what we call substituting. Substituting the previous equation del T over del T left hand side. Why we put del T over del T? Because this is T L plus 1, superscript L plus 1. That is what we want to find. That's why del T over del T always left hand side, because temperature respect to the time. And the right hand side, there is a K. K is the constant. The value K will be given. K, you just put it in front, and then you substitute the whole thing here. Write down, yeah? Del squared T del x squared is T superscript L I plus 1 minus 2T superscript L subscript I plus T superscript L subscript I minus 1 divided by del x squared. Now, you have to simplify this. You do it now. This T subscript I superscript L plus 1 left hand side. So the minus T becomes positive T. And del T you bring right hand side. It becomes K del T over del x squared, the common factor. This K del T over del x squared is called lambda. So lambda can be calculated using K del T divided by del x squared. This is the shortcut. So the equation that we need is T superscript L plus 1, the left hand side, equals to T superscript L plus lambda T superscript L minus 2T superscript L plus T superscript L. Can you get this equation, class? Slide number 7, yeah? Try to verify this equation, please. Yeah, Liu, can you get? Try now, please. Can you get the right-hand side? Anyone can answer me, please? Yeah, Mohammed, I'm done. So, what about others? One Amir. Okay, good. Muhammad Ali. Your phone. Can you mute the phone? Muhammad Ali. I can hear the sound. Yeah. Bakhtiar can. Can. Okay. Muhammad Ali, please mute your phone.
Okay, sorry.
Muhammad Ali. Okay. Thank you. Okay, please reply. All right. So you already have the left-hand side. What is the meaning of L plus 1, L, and right-hand side, T superscript L minus 2 superscript L plus T superscript L. All these terms we will explain in the next slide. So what we need is, of course, the lambda is K multiplied by T over del X square. Why we write this lambda shortcut? Because this lambda, you cannot straight away substitute lambda. You must substitute K first. So this equation looks nice, very elegant, very nice. It's like a well written form. Or if you don't like lambda, then you put K del T over del X squared. Doesn't matter. So the lambda value it will not be given. You have to calculate. What will be given is K 0.5, del T 0.75, del X 8.5, like that. So the lambda is not automatically will be given. You have to calculate. What will be given is K del T del X from the problem. So we need this equation. We need this equation for what? To perform the iteration. I equals to 1, I equals to 2, I equals to 3, I equals to 4. But the second, this first level, L actually stands for level 1, level 0, level 1, level 2, like that. So the L and I, you must differentiate. This is the confusing part, but it's not very difficult because this is all numerical method. So once you done the first iteration, then you already familiar, but you must perform the iteration first. Once you are familiar with the first iteration, you know already everything. Then the second iteration, third iteration, you just follow. And that is good thing about the numerical method. It's not you use another formula. No such thing as another formula. Only one formula only, but we do the iteration. So what is that, class? What is this all these terminologies? T and then superscript L, subscript I. But the lambda is already explained. Now the explanation is for L, capital T is the temperature, and subscript I. What is this? So in order to understand that, we have to know a little bit about this time and the distance. You see, you are solving the equation. The capital T is time x. Capital T is time x. So meaning The problem that you're solving is capital T, time variable, X variable. This is the problem. T stands for temperature. Small t is time, X is, we call it space, but that is the distance. This is the problem. That's why we call two spatial. Two spatial. That means the dimension t, time, and X is the distance. So this slide, I hope you can see the slide, number 8, yeah? We want to know the heat conduction equation in time and X domain. So this equation can be written for all interior nodes. What is interior nodes? You will see in the next slide. And then provides an explicit means to compute, this is the thing, compute values at each node for a future time based on the present value at the node and its neighbors. So this is very important, class, because you want to compute for a future time, the t. So, but we have to consider the present value at the node. What is the node and its neighbors? You will see in the next slide. And one philosophical information here is this finite different approach is actually a manifestation of Euler's method for solving ODE. There is a direct connection because it's already gone through a tremendous improvement. So if you want to know how it was developed from Euler's method, then you got to go and study very huge literature. So from ODE, how it depart to PDE. So
Hello.
you saw in,
Sir,
yes?
sorry for interrupting again, but your slide is not moving again.
Oh, slide number 8 now.
Right now we are in slide number 7.
7, huh?
Yeah.
So that means every time I have to, because my slide is, so we can this slide, sorry sir, but I think you need to share again every time you want to change the slide. Yeah. Okay. So every time. Okay, slide 8 now. Yeah, Dennis, we can't see the slide, sir. Sorry, sir, but I think you need to share again every time you want to change the slide. The slide is not moving. Stuck at Mohammed Dennis. Okay. All right. So slide number 8 is just explanation. Now we move on to slide number 9. So slide number 9. Can you see slide number 9? Slide number 9 is a computational molecule for explicit form. So you may wonder what is this diagram. This is what we call grid point diagram. So the cross sign is grid point involved in time difference, and the circle sign is grid point involved space difference, x. So in this case, the vertical axis is x. The horizontal axis is t. So in the previous slide, you saw the time. The next one. The previous one is L. The next one is L plus 1. This is the x-axis. Horizontal axis. Horizontal axis represent the time. Vertical axis, this is x. So the distance x minus 1, the previous one, and the xi is the current one, xi plus 1 is the next one. So the intersection, the cross and circle, is at xi, the current one, and the TL. From there, we move on to TL plus 1, the next one. So this is the grid point diagram. Because you saw the equation del T over del T equals to K del square T del X square. So temperature depend on the time, the output. And the temperature also depend on the distance x. So in this case, the T and X both are the inputs. And then you find the temperature. So now we move on to slide number 10. Yeah? Okay. Can you see the slide number 10? Now, 10, yeah?
Yeah, can, sir, can.
Slide 10, yeah? Okay, slide 10. Thank you, Purushotman. Slide 10 is the example. We saw it in the previous section, 5.1. But now we want to solve. So the problem statement will be lengthy because this one involves initial condition as well as boundary condition. Remember, yeah? Initial condition and then boundary condition. So that's why we have a very lengthy problem statement. So what is this problem class? Example 1, don't worry, the solutions are available. Use the explicit method to solve for the temperature distribution of a long thin rod with a length of 10 cm. In the previous lecture, we showed to you the rod from hot to cool. So the length of the rod is 10 cm. Now we must use the unit because the variables must have units. Otherwise, you will confuse which variable is which. So the length is 10 cm with the following values. The del x is 2 cm. The del x is the last time we call it step size for the distance. So that means from 0 to 10, the del x 2 cm means 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, like that. So there is a interval, yeah, we call it interval. So the interval for the distance, the x is the y-axis. X is the y-axis. You can draw the graph. X is the y-axis, 0, 2, 4, 6, 8, 10. And the del t is 0.1 second. Del x is 2 cm because the length is 10 cm. So the x naught last time you say 0, x1 is 2, x2 4, x3 6, x4 8, x5 is 10, like that. And the del t is the step size for the time. So from 0 and then 0.1, after that 0.2, and then 0.3, 0.4, 0.5, and so on. So the del t is 0.1 second. Now at the time t0, t is the x-axis, yeah, or horizontal axis. X is the vertical axis. X is going to the north. T is going to the east. So at time 0, the temperature, the capital T is 0. This is very important. This one is called the initial condition. When the time 0, the temperature of the rod is 0. This is initial condition. It's not written, but it is understood. Because this is not boundary. Just now what you saw, the grid is the boundary. You have the boundary actually. So this as T0, this is not clear. At the time 0, the temperature, the capital T is 0. So you must remember that. At the time 0, the capital T is 0. And boundary conditions are fixed for all time. All time means this one. The capital T at all time at x0 is 100 degrees Celsius. So x0 100 degrees Celsius. When x is 10, 50 degrees Celsius. This is from hot to cool. So at the temperature at x0 given, at x10 is given, but x2, 4, 6, 8 not given. Now you are going to find that. That is the objective of this question. Clear, class? The temperature at x0 is 100 degrees Celsius. This is given. And the temperature at x equals to 10 is 50 degrees Celsius given. So you have to find, now they're asking you find the temperature at T0.2. At T0.2 for x2, x4, x6, x8. But before you find T0.2, you must find 0.1 first. So today we just show you T0.1 first. That is today's lecture. So in order to perform the calculation, you need the K value. Without this, cannot. So K is given as 0.835. Write down, yeah? You can copy this problem. Please write down this problem. So your K 0.835, write down. Your del X is 2 cm and your del T is 0.1 second. Now you can calculate your lambda. That is how you want to calculate your lambda. Lambda equals to K multiplied by del T over del X squared. So we are going to solve this problem. Question is, find the temperature at T 0.2 second. So first you must find the temperature at 0.1. At T 0.1, at X equals to 2, what is the temperature? At X equals to 4, what is the temperature? At X equals to 6, what? At X equals to 8, what? 10, no need. 0, no need. Any question, class? Hello, any question? Now we move on to next slide. Can you see slide number 11, class, now? Hello? Can you see slide number 11? No, sir. Okay, slide number 11 now. Can you see slide 11? Oh. Okay. Slide 11. Slide 11. Okay, when can? Okay, slide 11. Now, for level, the level actually the L. First T.01. But the question is, they ask you to find 0.2, but not yet. We cannot find 0.2 yet. So the equation we need to calculate the temperature at time 0.1 second is this equation, which we already given to you, the T superscript L plus 1 subscript I, because this is L plus 1, the next level, left hand side, equals to T superscript L subscript I plus lambda T superscript L I plus 1 minus 2 superscript L subscript I plus T superscript L subscript I minus 1. This equation, we know that it is very difficult for you to memorize, but you can always refer to any text or any notes. So you no need to worry. This equation normally will be given. If not given, you will be asked to refer. So the lambda is the short form, because easy to put the value here and the equation doesn't involve any fraction. So that's all. So the calculation of lambda goes like this, class. All of you take your calculator now, because every time when you solve this problem, you must calculate the lambda. So the calculation of lambda is very simple. Take the value of K. You cannot create your own value. It's given already, 0.835. Put the value in your calculator now. and do the experiment. Yeah, this is what we call numerical experiment at laboratory. So the laboratory, in this case, you are using the instrument, what we call as a calculator. Of course, you can use iPhone or any device to calculate this, non-necessary calculator. Of course, you can use calculator in the internet as well. So 0.835 multiplied by del T 0.1 divided by del X squared.